All right. Transformers. Should probably tell this is a joke. So Transformers, as you can see, that was invented in 1831 as a way to, you know, uh, impact through this coils to, affect the electromagnetic field, and then be able to um, basically this is a device for the electricity transfer and other electric applications, where this was I think it's the initial movie from 27 about these robot revolution. Okay, so what is a transformer model? Transformer model, this is a kind of a very high level picture of it. It has some parts within this model where it gets inputs, and it will produce a output, and with the corresponding probabilities. And the whole thing is the transformer model. The first stage is called the encoder, which receives the input and builds the representation, basically extract the feature from this input and get that ready for the next module, which is the decoder. The decoder has a lot more things in it than the encoder. That's why it shows as a slightly larger. It used the representation that outputs from the encoder along with other inputs. This here is actually using the output from the past X number of windows to generate a target sequence. There are different types of transformer models, depends on whether you have both of these encoder and decoder or only one of them. And in fact, that's how we differentiate different large language models based on their architecture, whether they have both parts or just one of them. And we'll talk more about it. A little history of transformer. This concept was originally proposed in this 2017 paper. I have a reference here, you can read it. And then it has, has basically revolutionized these deep learning and breakthrough. Its breakthrough has led to many different important milestones. 2018, the first generative pre-trained transformer was proposed, and it was mainly used for natural language processing. Then 2018, the BERT model was designed based on transformer to produce better summaries of sentences. And GPT-2 was released in 2019. And then after that, there was another newer version of BERT model, and then T5, and then 2020, GPU-3 was released and was shown to perform very well on a variety of tasks without the need for fine-tuning. So there's a lot of things happen. And of course, after 2023, GPT basically show the world that how powerful it can be. And that's why that's this basically signal the start of the generative AI era. Okay, so transform model is, as we explained, has this encoder and decoder. But in fact, if we put into the context and connecting with what we said earlier about the tokenization and embedding, so this is really the first part we explained. And this is the input token context window that we obtain through the tokenizer. We use tokenizer to get its tokens. And through embedding, we will map these tokens, their IDs, into a X dimensional number, a vector. The vector will be the inputs to this encoder and also for the decoder as well. So from bottom to top, we have input token window that contains the prompt input tokens. Embedding maps that to a multi-dimensional vector space. And the encoder will produce the output to represent their features. And within this encoder, we have the self-attention layers. This is the important concept we'll explain next. These self-attention layers are used in both encoder and decoder. And then the decoder will be connected to this final output layer called softmax. Softmax essentially produces these sequence of tokens with their probabilities. And through different sampling strategy, the output will be chosen among from these candidate outputs. Okay, so this is the tokenizer model in more detail. This picture is the one from that important 2017 paper. So we start from here. The input encoding is the X dimensional vectors that you get from this input sequence. Then we have a additional function called positional encoding. This positional encoding is really to look at these input vectors, because each token, they may appear in a different location in a sentence. So that location information will be also kind of encoded as a part of the input. So instead of, let's say, 100 dimensions after the embedding, you may be adding another level of information, another dimension to represent the position of that token. So that's additional information you can add in it. And then it'll be put into a attention module. And just ignore the word multi-head attention. So in fact, it is the attention module or layer that has been replicated multiple times. We'll explain what we do that. But essentially, this is a neural network layer that built on self-attention mechanism. Self-attention mechanism, as we will explain shortly, is a way to kind of learn the relationships among the tokens that appear in an input sequence. And then after that, there will be a feed-forward network. Of course, this is some concatenation and normalization layer that will do additional, kind of take the output from the self-attention layer, do additional processing. The other major component or layer is the feed-forward. Feed-forward network is kind of more complex. We call it multi-perceptron, multi-layer perceptron network. It's different from self-attention. This is more like more conventional neural network layer. Could be many layers. And after that, we have another add a normalization layer. So this block is the block that typically will be replicated a few times. So for the paper from 2017, they actually have 6 times of this same layer. So they replicate this 6 times. And that will produce a output vector tensor as the input that you will feed into the decoder layer. The decoder module it's very similar. As you can see, they have multi-head attention, basically self-attention that replicate a few times, and then the same feed-forward layer. So that's part is similar. Before that, there's a so-called mask multi-head attention layer, which gives the module the capability of ignoring some of the tokens using these masks. And for this part, this decoder module, it can also take the output here as additional input with their position information as the input of this mask multi-head attention layer. So this is basically the big picture of what kind of neural network layers within this transformer model, and how it how they built it to learn information. Yeah.
The previous plot is the output at the top what's getting fed back into the decoder?
Yes. Yeah. So one key concept is this self-attention. So the multi-head attention is basically a multiple instance of this self-attention. So what is self-attention? Self-attention is a way to find out the relevance among different tokens. If we have an input sequence like this, let's hypothetically think that this input sequence is now tokenized, and we have these tokens. The student learns from the professor and her lectures. So these are individual tokens. So what this self-attention is trying to find out is that how relevant is this word or any word as respect to the other tokens in the same sequence. This example basically now it shows that for this token that we are looking at now, if we look at this token, how do we measure the relevance of this token with every other tokens in the same sequence? We highlight here professor and her here because this lecture, her lectures, is in fact the professor's lectures. So from that sense, this token is highly relevant to this professor. It's basically they refer to the same concept, same object. Compared to other tokens, for example, these lectures, even though these two are still relevant, but not as strongly as this her and professor. Because we know this her lecture is always together in this sentence, saying that is kind of who owns this lecture, whereas this her and the professor refers to the same person. So this is what we call attention. And self-attention is basically to calculate the pairwise attention so that the model has a way to learn their dependencies. So which token is the most relevant to any other token, and which one is less or least relevant to the other token. So that's the purpose of this self-attention. So how do we calculate this? Attention assigns a weight to the input tokens based on their importance relative to the generative task. So each task may have different weights. What we show here is that we have 3 tokens, and each token is now, you can see that it's embedded as a 4-dimension vector. So we have token y1, y2, and y3. So we have the value vectors here as the we use these embeddings of these keywords to calculate their attention value, which is represented using y. The attention is also a vector of the same dimension. The value vector, we have their initial values, and then for each of the weights for that, the word we're trying to find out. So we're trying to find out how relevant these 3 words are to this first token. We will use the value of these vectors and their weights. And of course, the weight comes from a different process. But let's say we know the weight for each of these vectors with respect to this token. So we will calculate by doing a attention function. So basically, we use the weight times with this vector, and then we add these vectors together. So it's the weighted average of the vectors in this input sequence, capital X, which has 3 tokens. So these weights basically represent how much the model attends to each input vector in X. And if you calculate, then this is the final weight average. It's the weighted number. And then that's the vector representing the attention. So the next question is, how do we know this weights? It's 7:40. Let's take a break. We'll take a 10-minute break. We'll reconvene at 7:50. Okay, let's continue. So we talk about this attention function. Essentially, it's to use the input vectors with corresponding weight to calculate the weighted average, which will represent the attention from that word to other words or slash tokens. So how do we get the weight? How do we get the weight? Okay, so if you think about the token that we are interested in as the query, and every other tokens that we are trying to attend to are used as keys. Basically, we try to use this query vector and the key vector to do computation. For this particular example, we're using a 3-dimension vector to represent these tokens. Then we apply this dot product operation on the query and the key. So if you basically we're doing this element-wise multiplication, accumulate the products. So that's the dot product operation, and then we can then calculate. In this example, we have a score called a compatibility score will be calculated. So for this key, the score is 0.42. And then this second key, the dot product will give us the value of 2.32 and so on. We can have the score for the third key is 0.96. So we have these compatibility scores. These scores are just numerical value. We will then apply so-called softmax function. The softmax function essentially takes a sequence of these values, then use this exponential function, and then do summation and divide the sum to calculate or to generate the corresponding number. This number is what we call the probability. So the sum of these numbers will be a 1, where each of them represents the probability or the degree of relevance in a sense. So the higher number will represent this highly relevant or has more attentions. So this final sequence of numbers, these are actually the weights that we use in the previous example to calculate the attention value for that particular key. So basically, these are the weights and how we generate these weights. So basically, we explain what is self-attention and how we use these dot products to calculate the weight so that we can use it to then calculate the attention. In this paper, 2017 paper, they used a slightly different attention called scaled dot product attention. So everything else the same, except that there's a scaling operation when we calculate the compatibility score and before we generate the softmax. So the softmax function will take the scaled value of these dot product. This is the dot product, essentially. It takes the weight of k dimension number. The square root of that will be used as a scaling factor because the dot product value can basically vary in a very large range, which will impact the final output of the softmax function. So with this weight scaled the square root of the dimension of vector k, we can reduce the absolute value of that dot product, and so that we can have this softmax function produce a more reasonable range of the probabilities / weights numbers. Well, before I move on to the multi-hat, so this is essentially the core self-attention computation in this transformer model. So we have these Q and K and this value as the input. This is the scaled dot product attention is the foundation of this multi-hat attention. So this part here is the scaled dot product attention. So why do we use multiple of them and call them multi-hat? Well, first of all, these essentially the same structure or same architecture in terms of the model. So the computation is very similar. And you can see the same inputs are given to these different hats. The purpose of doing this multi-hat is to capture different types of attentions. Just give you an example. Let's say in this text document that we have different verbs, and the verbs they may be followed by an object. So it may happen that the first head or the first copy of this scaled dot product attention tries to capture the relevance between the verb and the following object. Another head of this dot product attention module will capture the relevance among these different verbs. Because if you only have one head, or if you only have one copy of this scaled dot product attention, you may only capture one level of relevance. With multiple heads, you can have the capability to capture other type of relevance, because these different layers, the different heads, they operate independently. They started with different random numbers, and they are trained differently. And because the nonlinearity of these activation functions that embedded into these modules, they may produce different outputs iteratively. So in the training process, they tend to be learn different relevance. And also because they are independent, so they can be pay attention, perform the attention function in parallel, and they produce the outputs independently. And at the end, these outputs will be concatenated and generate the longer vector output to the final output layer.